Okay, so welcome to part 3 of this series of videos on BJTs. This is going to be talking about using a BJT as a switch. Okay, so I'm going to use the example on page 237 of your textbook. So basically, I'm configuring this BJT as a switch. That means what I want to do is that I have a voltage coming in here. Okay, I'm going to have a voltage coming in here, and because there's a voltage coming in here, I'm going to switch on this LED. So it's, instead of pressing your finger down on a traditional mechanical switch, I'm going to have a voltage in here. It turns on this LED. Okay, so acting as a switch is this BJT. Remember, I have a current coming in here, means once I have a current coming in here, I turn on the collector current flowing all the way down here, and this sort of acts like a switch, a floodgate, so to speak. And once I have current and voltages all coming down here, this LED turns on. So it acts like a switch. Now, in order for me to use this BJT as a switch, I need to be able to know what values of resistor I have to use at the base. So this base resistor kind of controls, this is like the control of how much current flows in here. Okay, I need to have a certain amount of current flowing in here in order for this to work properly as a switch. So I want full current, full power coming through here, and this LED will be its full brightness. All right. To use BJT speak, what I'm going to do is I'm going to drive it into saturation. Okay, drive saturation means I'm going to have the full amount of current flowing down here. Okay, so just remember that. So this is a calculation analysis of how I find what value of the base resistance I must use in order to have the full current and voltage and power flowing through here in order to light up the LED properly. Alright, so here we go. Now, I'm not going to start off at this branch. Instead, I'm going to start off at this branch here. I'm going to do the analysis on this branch here. So remember, Kirchhoff's voltage law, I'm going to start off with 5 volts here. And when I have 5 volts, every time it meets a component, in this case it's a resistor, there's going to be some voltage drop across here. So some voltage is going to drop here. So from 5 volts, some is going to drop. When it crosses the LED, some voltage is going to drop here as well. So 5 volts, drop some here, drop some here. And remember, in video 2, I told you there is a voltage drop across the collector and the emitter. So there's going to be another voltage drop here until it reaches 0 volts. Okay? So I'm going to analyze this branch first. Now, don't think about this branch yet. I'm just going to analyze this branch, and I'm going to tell you why I analyze this branch. Okay, so let's start off with 5 volts. So if I take 5 volts and I minus away this voltage drop, I'm going to use Ohm's law, V equals to IR, right? To find the V drop, I'm going to use V equals to IR. So I of the collector, R of the resistor here, which is 470 ohms. I minus away the voltage drop across the LED. In this case, it's given as 2 volts. This is the information given. The forward voltage of the LED is 2 volts. So this is 2 volts here. So I have to minus away the 2 volts. I have to drop another voltage here called the VCE at saturation. Okay, if you're wondering what in the world is saturation, remember this is the point where the full current flows down. So that's saturation. Basically, all it means is that I have the maximum amount of current flowing through here. Okay, so I want that value VCE here because it's the ideal, right? We want the full value of current flowing through here at saturation. Therefore, we take the VCE at saturation, which is 0.2 volts. And we end up with 0 volts here. Okay, so what I want to do is I want to find what is the collector current flowing through here. So the collector current flowing through here is 5 minus 2 minus 0.2 over 470. Okay. And you find out that after pressing your calculator, you can go and press your calculator, this will give me 6 milliamps. Okay, so I know that I have 6 milliamps flowing down as the IC, okay, the collector current. So this is where I tell you why I want to find out what's happening on this branch. It's like you're wondering, you want to find what's happening here, you want to know what value here, why are you going to find here? So this is why. Because I know that the base current is related to the collector current. If you remember the second video that I made, you'll know that the collector current is beta times of the base current. Okay, so now I'm using this information to jump to this branch so I can work on this branch. Okay, so I use this information to get me onto this branch. So I can find now what is my base current, which is IC divided by beta. IC is 6 milliamps and beta value given is 30. Okay, so 6 divided by 30 is 0.2 milliamps. 0.2 milliamps. Okay, so now I've got the current flowing into the base. So I've got a current flowing into the base now. Now I can analyze this branch. So I start off with the voltage at the V in, and they tell me that I'm going to switch on this LED with an input voltage of 3.3. Why 3.3? I don't know. Probably the previous subsystem will give me an output of 3.3 volts. So that's why they're thinking, okay, if I use 3.3 volts, how much resistor must I have here in order to turn on this to turn on the LED, okay? So that's the condition we are given with. We are going to work with this. So I have 3.3 volts. I'm going to have a voltage drop here. Okay, so I have to minus away the IBRB. Okay, so I'm at this point now, and in order to go back down to ground, remember in video 2 I told you there is another voltage drop here called the VBE. So I have to minus away the VBE, and then finally I reach 0 volts. So this equals to 0 volts. Alright, so let's fill in the numbers. I've got 3.3 minus the base current we found out was 0.2. The base resistor is what we want to find. The VBE value is 0.7, is given in the information here, so minus 0.7, and this will be 0 volts. Okay, so if I rearrange my equation to make RB here, I'll have 3.3 minus 0.7 divided by 0.2 milliamps, and I will end up with a value RB of 14,664 ohms. Okay, so but of course you won't be able to find 14,664 ohms exactly in the cupboard at the back. So you got to go to the E24 series, look for the closest value to this, and here's a tip, pro tip, yeah. So what you need to do is to choose a slightly lower resistance. Why slightly lower? Because having a slightly lower will ensure that we confirm will drive this fella to saturation. If you choose a slightly higher, it might not drive this fella to saturation. Okay, so remember, from the E24 series, choose one that is slightly lower in value, the next lower value. All right, so this is how it works as a switch. So please go and study this again, work it out yourself in your textbook, and make sure that you are able to find out what is the RB value by yourself. So just to summarize, this fella works as a switch. I have a voltage here. That means current is going to flow into the base, and once I have a small little current flowing into the base, boom, it opens the floodgates for all the current to flow through the collector and down through the emitter. Along the way, as it's flowing, it's going to turn on the LED. That's why it acts as a switch. Okay, turning on the LED here. And in order to turn it on to full brightness, to get it to saturation, I need to bias this fella to kind of find out exactly what resistor value I need. And then to find out what resistor value I need, I do this calculation, brings me down to this branch, and I can find out what is the base resistance. Okay, so watch this video again if you are slightly unsure, but you need to know how to bias to do a circuit analysis of a BJT when it is acting as a switch. Okay, so this is the end of this video. Next video I'm going to talk about using the BJT as a amplifier. All right.